Buongiorno a tutti e benvenuti.
Good morning, everybody, and welcome to this meeting with two of the major protagonists and initiators of the Planck project of the European Space Agency. It's the most powerful telescope ever conceived, a sort of time machine, 1.5 million kilometers in orbit around the Earth, in order to have a window on our universe and trace back to all those structures which are formed in the universe, the stars, the planets, the galaxies. Today we will be listening to the earliest observations by Planck. The meeting in Rimini has always posed us in front of new scenarios from scientific research, ensuring and guaranteeing to us the possibility of sitting in front of great scientists and see the world with their eyes. They are the tip of mankind exploring space and new possibilities for our horizons, and sharing with us what they have lived and discovered. They allow us to discover a greater truth. Last March 21st in Paris, in an international press conference, the first pictures, the first cosmological maps of the Planck Institute were presented to the world. On the press of the whole world, we saw a map of the newborn universe with a very high definition. To all scientists and cosmologists in the world, it was like landing on an unknown continent, something absolutely extraordinary, a feat which has enormous scientific meaning in terms of confirmations of conventional cosmology, and also in terms of new discoveries on the ingredients of the cosmos, raising questions which have many consequences scientifically and which will actually involve our cosmologists in the future. This required thousands of hours of work to an army of brilliant researchers from all over the world. Our two guests have for more than 20 years shared deep friendship, leading the mission, especially the low frequency instrument, which is one on board Planck. Their common experience with George Smoot, a Nobel laureate for physics in 2006, who we were honored to have in Rimini in 2007, allowed our guests to meet here today. So warm thanks to Nazzareno, Mandolesi and Bersanelli. Let me introduce them to you. Professor Nazzareno Mandolesi is Professor of Physics at the University of Ferrara. He is a member of the Board of Directors of the Italian Space Agency, and he is an ENAF associate. He started first by studying cosmic rays at high energy in the world of the infinitely small, to then go to the infinitely great, the universe, through the study of the fossil of cosmic background radiation, the first light of the universe that we will hear about today. In the 80s, he made an experiment on the cosmic background in the White Mountain Station, California, in cooperation with Professor Smoot. Now, Professor Mandolesi is the principal investigator of the low-frequency instrument of Planck, and he is the head of an international consortium of universities, research institutes, and companies. And during the mission, this involved more than 1,000 people. At the present time, the consortium, Planck's consortium, includes more than 500 engineers and researchers for the operability of the satellite for the analysis and interpretation of data. He was the director of a CNR institute, now ENAF, and he was the director of this institute from 1994 to 2010. Starting in 2004, he was concerned with technological transfer, and within ENAF there is an international center for technological innovation and then service for technological innovation, and he was in charge of it until 2011. ENAF in 5 years deposited 20 patents and 5 spin-off societies or companies. Thank you and welcome, Professor.
L'altro nostro ospite di oggi.
The other guest we have today needs no introduction. If these is the meeting in Rimini seemed to be a branch of NASA or MIT. This is due to his passion for scientific dissemination and discoveries and his ability to focus not just on the subject of research, but also mankind and the protagonists of research. Thanks to him, we have learned how to look at the stars in a different way, and also those looking at the stars. Let me introduce to you Marco, who is a professor of astronomy and astrophysics. He's the director of the doctorate school for physics, astrophysics and applied physics at the University of Milan. Right from the beginning of his career, he's been concerned with cosmology, especially measurement of the microwave cosmic background, the first light of the universe. From 86 to 91, he worked at the Loris Berkeley Laboratory, University of California, with George Smoot, participating in 2 scientific missions in the South Pole, in the Antarctic base, for measuring the spectrum of primordial light. And now he is instrument scientist, deputy principal investigator of the low-frequency instrument Planck, and he is a member of the Planck science team. Apart from the many scientific publications, he is also the author of many publications. He is the scientific director of EURESIS, the scientific society with which he promoted didactical exhibitions that we all know, conferences, international meetings on interdisciplinary topics. Since 2012, he is the chairman of the Sacro Cuore Foundation for the Education of Young People. Thanks, Marco, and welcome again. I would like to ask Marco Bersanelli to start from the image which has gone throughout the world, the skywide image produced by Planck. How was this map developed? What about the data collected 15 months after its being launched? Thank you, and welcome everybody. Hello. It's really a great pleasure for me to tell you something today about 20 years that have elapsed since the launching of this project. Actually, together with Nazzareno, we have shared this long history. What is it about? Let's start from an experience which is common to all, the sky. A starry sky which is above us and strikes us because of its vastness, the enormous amount of stars which fills our heart when we are really in a dark night. And this is the Milky Way. As we know, it's composed of billions of stars that cannot be seen one by one, but they are shiny and form this arch in the sky. All these stars, the ones we see one by one, and also the light of the Milky Way, are part of our galaxy, of a family of 100 to 200 billion stars. But if, with a powerful telescope, we analyze what happens in depth in just a small portion of the sky. In this animation, you see the starry sky, you see Orion, the constellation of Orion, and this is the Hubble Space Telescope. And here we'll zoom in this area where the Hubble telescope obtained the deepest image of the universe and galaxies. These are stars of our galaxy, but from now on, we are getting out of this galaxy, of our galaxy, and every dot you see is a galaxy containing 100, 200 billion stars, and there are other galaxies. This is the Hubble field. Take 1 cent of euro and put it at a distance of your arm, and there you see galaxies. They are all at a different distance from us. Those that are farther away are 10, 11 billion light years from us. This means that the light has taken 10, 11 billion years to reach us. So those galaxies are as they were that time ago. We know that the universe, this ocean of galaxies, is being expanded. In the past, the galaxies, I think, had to be closer to each other. And we know that the moment in which those galaxies were very close to each other, the beginning of the expansion history of the universe dates back to approximately 14 billion years ago. So those faraway galaxies are seen in a young universe compared to the 14 billion years that they are now. So we want to get closer to them, closer to the beginning of the expansion of them. This is possible thanks to a basic discovery made by these two American radio astronomers in the 60s. This is a radio telescope. They actually realized that from regions of the sky where you don't see any source, you just see the black background of the sky, that far away land sends us very weak light with the same intensity, more or less, in all directions. This light has traveled throughout the history of the universe, 14 billion years, and therefore it comes from the moment in which the universe had a very high temperature and density. This is the microwave cosmic background, the first light of the universe that we can really study very precisely thanks to Planck. It's a precious, marvelous fossil. And thanks to this, we can establish direct contact with what was happening at the beginning of the history of the universe. And this picture summarizes what we have said. Here, each dot is a galaxy. We are getting farther away in space and also going back in time compared to our point of observation. Each point is a galaxy. We are surrounded by billions of galaxies, but down there where you see the black part, which is the background, you discover that there is a very weak light which can be observed at the microwave length. And this light gives you an image of how the universe must have looked like at the beginning of its history. This is a discovery of the 60s. Another major step was made in 1992 when another precursor satellite called Cosmic Background Explorer, led by John Mather and Smuth, developed the first map of the entire celestial sphere. You see this primordial light. It's very uniform, but not perfectly uniform. These spots show that there is a different light intensity depending on where you see the light in the sky. Initially, the universe was very smooth, very much the same, very simple, but Corby, for the first time, measured that there was some unsmooth portion. It is as if in a lake there were very small wrinkles or crumples, which actually are the origin of all galaxies and groups of galaxies. It's areas where the gravity is stronger than elsewhere. At that moment, the idea came of making an additional step forward, have this same image of the primordial cosmos and sky, but in a more precise and accurate way. And this was the beginning of Planck. This was how Planck was conceived. But, you know, you may wonder, why all this? What is it that all this teaches us? It's certainly not simply for the sake of seeing an image or a picture. What is it that Planck can show more than Corby? Gravitational signs of structures forming the universe the way we see and observe it. I'm now going to show you some technical slides, but don't worry. You can easily grasp the concept. This is a very brief representation of all the information you can find in a map like this. You know, these different intensities may be statistically reconstructed to form a curve like this. This is an angular scale, that is how large the regions we consider are, and this is contrast, how high the wrinkles, the small waves on the image are. The map you saw before by Colby only shows a small part of this information. The yellow curve is what theory predicts as to how distribution must be like or expected is expected to be like, and I'm referring to the distribution of the waves on the surface of the image. You see that what this curve may tell us is still unknown. According to Colby, there is a yellow curve of this type, and these are the experimental dots, but Colby also tells us that it's important to further investigate the cosmic background to get all the information, to understand all the information which is contained in the peaks and depressions of this curve. Why is it so important to measure that curve? Because the details of the curve depend on some fundamental parameters in cosmology. Actually, in general relativity, this tells us how our universe behaves, what its ingredients are and its geometric properties. Therefore, precise measurement of this curve allows us to capture these parameters, as Nazzareno will tell you later, and they tell us a lot about the history of our universe and its structure. Planck started way back in '92 with the discovery of anisotropy by Smoot and Kobe, and then since then more than 20 years have elapsed. We launched the satellite in 2009. We're here in 2003 and 13. We've got the earliest information. The satellite is coming to the end of its career. This is all about men, sacrifice, hundreds of people, work, hard work. This is a picture of the Planck team. It's the core team of Planck, people working full-time. Here you see the names, one by one, of the almost 400 scientists working at this feat, at this enterprise. As you can see, also from the human standpoint, it's an extraordinary adventure. This journey has been ongoing for more than 20 years already in order to get to this objective. This is the satellite, 4 meters at the base, 1.5 meters is the length of the telescope. You see this mirror which collects or captures the light which has traveled for so many years, and then the light is reflected on the focal plane. You see this box which is here magnified. These are the eyes of our instrument. Then you have the antennas, and everything is then brought to the right temperature, and we can capture the radiation. Italy and France are the leading countries in this consortium, which includes many universities and institutes throughout the world. Now, in just 1.5 minutes, I'm going to show you the work of 20 years and more. The construction of this jewel of technology, Planck. You see the focal plane I showed you before. These are the wave guides which take the low-frequency instrument signal to the lower part of the instrument. These are 3 screens separating the hot part from the cool part of the spacecraft. This is the first of the 3 coolers. They act as refrigerators, cooling down the focal plane. This system is at 20 kelvins, 20 degrees above the absolute zero. The second cooler brings the temperature to 4 kelvins, and then you have the dilution cooler with helium-3 and 4 in these spheres, so that the center, the core of the focal plane is brought to 1/10 of a degree below the absolute zero, 273 degrees below zero. This is something exceptional in space. You see the subsystems, the subsets, the service module. Here you can see the electronics guiding the performance of the amplifiers. This is the sun panel, and here you see the telescope, the secondary, the primary telescope, the screen which protects everything. This is the launching of the satellite on May 14th, 2009. It was a great emotion for all of us. And then the satellite reached a great distance from the Earth. This is another critical moment, the separation of the satellite. This is an animation of the satellite, of course, but here you have separation from the support. There's a spinning which is imparted to the satellite, and this is fundamental for the way that the satellite has to observe the sky. Once a distance of 1.5 million kilometers from the Earth is achieved, what does the satellite do? Well, it's been spinning during all the time it's been in orbit. Once a minute, its telescope scans a small part of the sky, but since it follows the Earth in its motion around the Sun, little by little it changes the angulation with which the telescope sees the skies. So little by little it covers all the celestial, the sky sphere. As you can see in this animation, this simulation shows it very clearly. You see the small signal differences that you see above and below this sphere. It's the markings of the first light of the universe. And you also see this red portion, which is nothing but our galaxy. Our galaxy, you see it here in the visible wavelength. It emits microwaves and sort of contaminates the part of the sky we're interested in. Planck contains many such eyes of different sizes so that we can see different wavelengths. This is most important to be able to detect the radiation from the near universe of our galaxy as if it was some kind of dust on a window, and discern it from the one we are concerned with, the one that comes from the cosmic background. You see low frequency, the low frequency instrument, the one that Nazzareno and I have been concerned with for many years. These are the larger ones. And then you have the high frequency instruments that are smaller eyes. This means that we work at higher frequencies and the other eyes work at lower frequencies. Now, in the time which is left to me, I don't know how much, but not very much, I suppose, I'd like to show you some data. I'd like to show you the earliest results. I hope I was able to explain what Planck is all about. I'm now going to tell you about real data. We've been gathering them for some time already. I'll show you 9 maps corresponding to 9 wavelengths generated by Planck. In every one of these pictures, you will see the eyes producing that map. We'll start from the larger wavelengths and smaller frequencies, 30 gigahertz. This is the frequency. We're expecting that the pollution, the sort of dust on the windscreen is quite high. This is the red curve, and it shows how important the galaxy is, and the 9 gray bars are the wavelengths of Planck. This is real, actual data at the lowest frequency, 30 gigahertz. You see that the pollution of the galaxy is rather strong. Of course, we have to get rid of that pollution and contamination in order to be able to measure the primordial background in a very accurate way. We'll now shift to a higher wavelength, and you see that the galaxy has reduced. At 70 gigahertz, you have the least of emissions. And then from here on, it starts increasing again, 100, 143, 217 gigahertz, 353, 545, 857. You see here, the cosmic background is no longer visible. It's just dust. Why do we want to do all this? Because on account of all this information from these 9 maps, we can discern and detect the radiation which comes from local contamination and the one which comes from the deep universe, which is the one we are interested in. To give you an idea of what it is about, in this short animation, we really see the sense of what we're saying. Basically, we have a raw map containing all the information from our galaxy, You even have information on punctiform galaxies. They can be separated from other galaxies. Well, you know, it's actually not that simple. It's not like peeling off a map as we're doing now. There's a much more complex process, of course. This is the dust of our galaxy where new stars are born. And here you see the primordial radiation, which is really our true goal. It's the radiation which comes from the beginning of the expansion of the universe. This is no longer simulation, this is no longer animation, this is the map produced. Basically, all the work around Planck, with 20 years of work, was dedicated to developing a sort of camera whose task was to take a snapshot like this. This is the most accurate, the deepest image ever produced of our cosmic origins. This was released in a press conference on March 21st, 2013 at ESA, Paris, and the day after it actually received coverage by many newspapers. Actually, some Italian newspapers have not considered this. I'm not polemical, but it's rather significant of the fact that Italy has contributed to the mission, yet there was no coverage by the Italian press. Anyway, before giving the floor to Nazzareno, I would like to stress a couple of things about this map. You see 3 numbers. Don't be scared. These are important numbers saying very important things. Let's start from the one in the middle. This tells us about the contrast level between these more intense areas in red and the less intense areas in blue. 1 part out of 100,000. This is what Kobe had observed already, but with less accuracy. Instead, Planck generated all this with great accuracy and detail. You know, contrast coincides, intensity contrast coincides with gravity contrast. You know, it's like seeing the galaxies being conceived in their existence. You know, in this universe, the galaxies did not exist yet. There was nothing, virtually nothing. There was some kind of wrinkle, some small waves on the surface, leading to gravity, and gravity would then give rise to galaxies. And this number actually tells you how intense that waving or that wrinkling was. This number on the left is the time, the age of the universe when the light started its propagation towards us. We have a universe of 14 billion years, and the Planck instrument measured this number very accurately. That is the age of the universe. But the moment when the light was sent off is 380 billion years ago, like a baby compared to an adult. The third number is the most impressive one. It's the most speculative at the same time, too. It tells you the time in which, according to certain theories, and we are a bit extrapolating from theory, those wrinkles, those small waves had formed, and we're talking about a very small fraction of a second, 10 to the minus 35 seconds. Now, Planck's goal was to measure that yellow curve and the peaks in it with great precision, because from those measurements we wanted to draw some parameters. Here it is. The red dots are the measurements, and the green curve is what is envisaged by the theory with parameters which are now rather clear. And Nazzareno will expand on this. Let me finish now with a sentence by Max Planck, to whom our satellite is dedicated. He was one of the most important physicists in history, and he was also one who could accurately describe the experience of research and inquiry. This is how he described the position of scientists, people wanting to investigate reality. He said, those that have reached the state of not wondering about anything anymore show that they have lost the art of reasoning and reflecting. Thank you very much. Professor Mandolesi, what have we learned from these maps? What are the confirmations provided to classical cosmology, and what are the cues for future research? Thank you very much. First of all, I'd like to thank the organizers for giving me the honor and privilege of speaking here at this meeting in Rimini, which I have always highly appreciated and which has always surprised me because of the large amount of young people and the enthusiasm shown by everybody in attending and organizing it. Thank you very much for your applause. Now, before covering the topic of how important modern cosmology is at the moment and how important it is that it turns into an exact science and it's no longer just philosophy. It started becoming a science in 1929 when it was discovered that the galaxies are going apart in the universe. Now, before talking about Planck's map and what it means, let me make a short overview of nature and creation, as well as their beauty. I would like to say, to start with, I'd like to raise a question to start with. Can this perfection in nature be the result of chance? Flowers, beautiful images from nature, butterflies, animals, and so on and so forth. A sweet puppy, and also forest animals. They are not at all scary in this picture, or turtles and birds, or these enormous marine stars. Finally, our marvelous Earth seen from the space station. Well, part of it, of course. Isn't all this marvelous? Marco showed you the sky already. In a starry night, in summer or even winter, on top of a mountain far from the light pollution of the cities, or in the middle of the sea, you probably have looked at the sky to observe these wonderful sky and stars above us. You've probably seen this streak going from one horizon to the other. Some people would ask me, is it cloudy? No, it's the Milky Way. It's our galaxy. That shiny streak which crosses all the horizon is the Milky Way. And also my favorite impressionist, Vincent van Gogh, painted this wonderful starry night on the river Rhône, showing the stars. The day in which he painted it, the stars were really in that position. This cannot be the result of chance. And now the vault of the sky. Marco showed you the picture in 2 dimensions. The sky vault surrounds the Earth. It can be represented in 2 dimensions. and the cosmic background map and the anisotropy map can also be shown in 2 dimensions. Please note here that below you have what the previous NASA satellite saw. It was launched in 2000 and completed its mission in 2009 when Planck was launched. Below you see the detail of a sky portion. You see that the same disuniformity of the cosmic background are seen very clearly in very much detail, and this is very important. WMAP was not able to show this as well as the Planck in such a good way as the Planck system did. And also COBE. You see these small distortions of the primordial light of the universe. The least intense parts are some billionth of a degree. And you see that Planck took this picture in a much better way than any other satellite before it. And what does this map tell us? Which information does it contain? The really wonderful thing about it is that this map shows us what the state of the matter was at the moment in which the first light in the universe was emitted, 380,000 years after the Big Bang, 20 hours in a life of a human being. It's like a baby born 20 hours later. We know our universe. We have a picture of the universe as if it was a baby 20 hours after his or her birth. And from this map, we can see what happened, or we can try to imagine what happened before. What Marco showed you is this curve. This is the anisotropy power spectrum. It's a very difficult word, but forget about it. What I would like to show you is that the errors are non-existing on the points of this map. Sorry, I can't use the pointer, says the speaker. I'd rather not use it. Anyway, the errors are non-existent apart from the left side, where you don't have instrumental errors, but errors of nature. They're called cosmic variance. They're due to the fact that from this galaxy we can only observe one universe. We only have one representation. If we went to another galaxy, we would have a different spectrum and image of that. Those are natural errors that cannot be eliminated. As I was saying before, that map represents the state of matter in the neonate universe. The points where matter is more dense are the signs of structures that collapsed because of gravitational instability. And gravity is what really dominates the universe. This is the anecdote which is told of Newton, who said that the force which dominates the Earth is gravity, and this exemplifies what I am saying. Now, concerning the map, what does it tell us? We can see how the galaxies, the stars, the clumps of galaxies have gravitationally formed, but we can't follow them step by step or point by point. What we can do is use powerful calculators to simulate what is happening. You see that the dominating force is gravitation, but you also have pressure. And you see that from those seeds, an aggregation of galaxies has formed. The Milky Way includes 100 billion stars. And the nicest thing I can tell you about is a journey which is the result of a simulation. Usually we use simulations to see whether they correspond to what is predicted by the theory. This is a journey on board a photon which travels at the velocity of light. And this journey takes us around ourselves for 7-8 billion light years. This is the universe we would see on board of the photon. Isn't it marvelous? We would then reach aggregations of galaxies, filaments, and go round them. What about other information provided to us by the Planck satellite? Certainly, it provides us with a very detailed picture of the first light of the universe. It tells us how light and matter are so connected to each other. We'll see this later. That first light of the universe is something we receive as it was then, 380,000 years after the Big Bang. The photons have then not interacted with matter the way they did before. So when expanding itself, the uniform has only cooled down. What we see today is the primordial light of the universe at 380,000 years, but cooled down 3,000 times. It used to be 3,000 degrees Kelvin. It's now 3 degrees Kelvin, less than 170 centigrades, but the structure is the same. What else does this map tell us? It tells us about the geometry and topology of the universe. The map tells us that the universe follows a certain rule. It's flat. It doesn't mean it's a sheet of paper, but it means that the laws of the geometry that can be applied to it are Euclid's laws of geometry. Planck confirms that the universe is flat. We'll see what its fate could be like. Another piece of information obtained from the map is the composition of the universe in a rather detailed way. In this pie chart, you see that only 5% of the universe is known. The rest is dark matter or dark energy. These two parameters are both unknown. What is dark matter? We don't know. Dark matter has the same chemical composition, is part of our chemistry, but it's not baryonic matter. We're made of baryons, the protons and neutrons of an atom. Protons and neutrons contain 3 quarks. This is baryonic matter. hard matter doesn't, dark matter doesn't interact with light, so we can't see it. This really suggests many insights. You have then the theory of supersymmetry, which says that the origin of this matter could be symmetrical particles of the baryonic elements. We see it because it distorts light. Planck, for the first time, saw this effect, the effect of light distortion due to the matter. This actually is a powerful verification of Einstein's relativity theory. This is the map simulated with the distortion effect. I don't really want to be too technical, but for the first time Planck observed this effect. This effect is also visible in the individual galaxies. If we wanted to measure the galaxy which is here marked with 1, and if we were at point 3 on the Earth, we would have a vast gravitational field in between. At that point, space and time would be distorted with a lens effect, and the light would be obliged to following the pathway of distorted space and time. This is an example. This is a cluster of galaxies called Abell 2218, and the lens effect one can observe is that there is a sort of doubling of the source we are observing, or a sort of melting of it, or both. The lattice-like structures around the main galaxy are just a doubling of the main galaxy we are observing. I talked to you about relativity, so let's explain what special relativity is, and I apologize to those that know this already. We live in a universe which has the space-time dimension, not only space or time. If you ask me what time is, I can tell you that time is one of the 4 dimensions of this universe, and you know the dimensions of space already. Considering space and time as one single entity implies effects that are well known theoretically. For example, reduction of length and extension of time. For example, if I observe at the same time 2 trains leaving from the same place at the same time, for a photon traveling at the speed of light, the 2 trains are not seen as traveling together because it travels at the velocity of light. And then you have the famous formula E equals to mc to the second, to the square. Einstein realized that space and time can move photons along this distorted pathway, as is clear here. You know, here we are observing a true galaxy. There is a big mass distorting space and time, and we are observing it in the wrong direction. Now, dark energy, this is even darker than the dark matter. It accounts for 70% approximately of the density of our universe. What is it? What is obscure or dark energy? A hypothesis, according to conventional cosmology, is that it is acceleration, also observed with supernova. Acceleration of the expansion of the universe. You know that the universe expands at a speed of 70 kilometers per second for two galaxies at 3.2 billion light years from each other. This was established by Planck. The magic number was 74 before. And also, if you recalculate with supernovas, encephalis, you obtain this. This could be theoretically explained by what Einstein added to the inclusion governing the universe, the lambda cosmology constant. Einstein himself described it as his biggest mistake. In Einstein's times, there was no expanded universe, but a static universe, and Einstein was forced to adding this lambda cosmology constant. Otherwise, his universe, his equation in the universe would have caused it to collapse too quickly. Conceptually, this cosmology constant is the one which could explain dark energy, but if you calculate it, you find a value which is 120 orders of magnitude smaller than one expects. So Planck measured lambda with numbers, and a completely different number was obtained from the previous one. Some more information from Planck. We have information on cosmic radiation, not in the initial, very early conditions, but also much earlier than that, as close as possible to the Big Bang. Now, I would really need a pointer, and I hope I can use it correctly. This is what represents our current standard model of cosmology. You start from the Big Bang. We have 10 to the minus 30 or 50 seconds, so in a very, very, very small time. And then you have expansion, very, very fast expansion of the universe. The points which existed before traveled at a speed which was higher than the velocity of light. Then, at the end of this period, the particles formed, and CERN saw the Higgs boson, and then the particles mixed in a very quick way and rapid way, and this became a fog. Then the universe further expanded and reached a temperature of 3000 kelvins, in which atoms and electrons formed or joined, forming the first atom of hydrogen. As you saw in the simulations, because of gravitation, some hundreds of thousands of years after the Big Bang, the first galaxies, clusters of galaxies and stars started to form. In Planck's map, there are some abnormalities which are not statistically significant, like this, for example. As you can see at first sight, this map is not uniform. There are areas where the light which is emitted is much less intense than other areas. This doesn't really have big statistical significance, but if this was true, we might imagine new physics. Some reflections, physical reflections on particles. You know, the physics of particles with the current accelerators reaches some fractions of a second after the Big Bang. With a cosmic background, you can go back even to times closer to the Big Bang. particle physics and cosmology have to be integrated and have to pool their results. Some more models apart from the one I showed you. There could be one universe only. There could be an infinite number of universes, or even it might not be true that we live in a 4-dimension universe, but it could be 10-dimension universe, the universe of strings. Marco already showed you the press coverage. Well, we also had the first page of the New York Times just below the headline. As the Americans say, if you have the part below the title, it is as if you had gone up the highest skyscraper in the world, but it doesn't bring you luck. Kalsansky, the discoverer of astronomy, worked for Bell Telephone. And in 1932, he discovered that there was a signal in the sky, and he discovered this by making measurements of connections at certain frequencies. And he discovered that there was a signal synchronous to the rotation of the Earth. And his discovery appeared on the first page under the headline of the New York Times, and a couple of years later he had to change his job. This was just an anecdote. Now, some final observations. As you saw, Planck's map reflects 15 months of observation, but there are still more to come. We have not yet analyzed polarization of the cosmic background. You know, it's like your Polaroid glasses. If you put them like this, you see certain reflections. If you put them at 90 degrees, the reflections are no longer there. If Planck observed a signal emitted by primordial gravitational waves, he would have discovered primordial gravitational waves. Let's keep our fingers crossed. We will know next year. I'm not astonished. I'm not surprised. Some people say that quantum fluctuations taking place during the period of inflation are responsible for the universe that we currently see. I'm not astonished that they can be accidental, but the thing remains that we still have to wonder about the very beginning. Why was it there? Who is it that ignited everything? I don't want to go on this. Marco and myself researchers. To us, it's important to do our job with patience, honesty, enthusiasm, and never give up. Let me conclude by showing you the 100 institutes, more or less, who participated in this adventure of ours, which has not yet been completed. And now let's really conclude on a maxim by Einstein. No experiments can show that I'm right. No huge amount of experiments can show that I'm right, but one single experiment can show that I'm wrong. Thank you.
Ecco, adesso farò delle domande ai nostri.
I will now ask some questions to our guests, and I'd like to invite them to answer shortly. Professor Mandolesi, it's taken you 20 years before getting these results, involving many scientists and researchers. Why did you embark on such an enterprise? Well, the motivation is always curiosity and looking ahead. The anecdote I told some students yesterday was how Planck, the idea, developed. Well, it developed in '84 when I was working with George Smoot. George said, you know, we need to see the cosmic background and what is there. We just need a space mission, and we just need the right sensitivity to observe what there is there. He submitted the right proposal to NASA, and COBE was launched, and anisotropy was identified and detected. We have ESA in Europe. The success rate of ESA measurements is very high, 100%, but it takes time. But we did better than the previous satellites. It's taken us 20 years, but we got there. Marco, a question to you. What were the reasons why you embarked on this adventure, and what are they still today? Let me add something different. Of course, curiosity is basic and fundamental, as Nazzareno said. Something that was very important to me was sharing. You know, the people you work with contributes very much to the success of one adventure, because you share curiosity and passion. I'm thinking of the young students and researchers with whom I work in Milan. They look at you with even greater curiosity. They give you more or additional prospects and outlooks, and this is decisive when you embark on such feats. You, at the meeting in Rimini as well, you know, the fact that you wait to see so many friends is really very important, because if you are an explorer, for example, you always have a desire to go back home and tell the others about what he or she has seen. It's part of the motivation of this work. Well, who knows how many things have happened throughout the years in this adventure. Can you mention just one, the most impressive one? To me, it was certainly the moment in which Planck was launched. It was really great excitement and emotion, perhaps only second to the birth of a child, one's own child. You know, it's just a matter of 10 seconds. The rocket with which it was launched to the space has a conventional engine which is turned on and has to be switched off after 10 seconds, and then the rocket's propelling fluid are activated and you can't go back. Those were the 10 most exciting seconds in my life. And apart from this, what about you, Marco? Well, apart from this, another incredible moment in time was a few weeks after the launching, when Planck reached very low temperature levels, and as you saw, it spins, it revolves around itself. So if the instruments work, well, so far everything had proceeded well, but perhaps the electronics might not have survived the vibrations, for example, of the launching. There's a first moment after some weeks in which the instrument is switched on and Planck sort of opens its eyes. So if everything functions properly, we expect to see a slightly modulated signal, one which is correlated with the rotation, with the spinning. We know that the microwave background has a global asymmetry due to the fact that the Earth moves in a certain direction in the local universe. But what matters is that, you know, when we saw the data when we saw this modulation, you know, it was like saying after birth, you hear the first cry of your baby. That was also very important for me, an important moment. Now, what was the most stressful moment? I need to ask you this. When did you think that the project was at risk, that you were about to lose everything? I remember this very vividly. I remember that day. It was July the 28th, 2009. Planck had already reached its destination, 1.5 million kilometers away from Earth, and the subsystem validation process was ongoing. Everything was working perfectly. We all decided to take some vacation. Me too. My wife said, well, this year we're not going to Croatia. We're not going to cross the sea, but we will sail along the shore. I had just left. We were in Cesenatico. I had only traveled a short distance. Then I had received a call from the ESA center in Frankfurt, or close to Frankfurt, and they informed me that the cooler, the 4 Kelvin cooler, which is a basic element in the whole chain of Planck, stopped working on its own. What shall we do? We need to contact everybody. Marco was on top of a mountain. My French colleague was in the Caribbean. All the others who could take decisions were not there, so the only one was me. That was the end of my vacation, which only lasted 1 day. At that point, I started contacting all the engineers, all the industry, etc., and we decided that the only thing to do was wait 1 day and switch it on again. It was switched on, and since then it has never switched off. What about you? I remember a scene a bit before the one that Nazzareno told you about. I don't remember the day. I remember very vividly that I really experienced a sort of dramatic situation. We were in Milan, in the former Laben, where the instrument had been tested and calibrated. It was complete, it was calibrated, everything had worked properly, it was brought to the low temperature, etc. There was just one final formal test at room temperature where you would simply turn on all the instrumentation, then you had to pack it back and send it away. You know, it was just one final formal test. It had to go right. So we turned on the instruments. Out of 22 channels, believe me, 12 showed no signs of life. At that point, I sort of got paralyzed, even mentally, you know. I could not understand how to go on. I didn't know what to do. I remember that some of the youngest in the team started to understand what it was all about. We understood what the problem was. Thanks God, it was something really very trivial, but not easy to understand. We solved the problem, and after launching, out of 22 channels, 22 operating well. And while we are here, the low-frequency instrument is still alive. It has lived twice as much or as long the life it was supposed to live, and it is yielding good results. A more demanding question. The subject of this research, universe and its origin, affects one religious question as well. How is this relationship perceived? scientifically, what's your experience, and how do you consider the connection between scientific research and faith, Professor? In the scientific milieus, and Marco can confirm this topic is not dealt with. You know, science and faith belong more to the personal choices. As far as I'm concerned, I reread the first verse of Genesis, which basically says, in principle, the Lord created the world, the sky and the earth. It's a problem of faith. Those who believe also believe in this first verse of the Genesis. Those who do not believe say that everything that cannot be demonstrated is not true. This is my perception, but at human level there has always been, in my experience, and I have a considerable experience, there has never been open confrontation, probably because of a privacy reason. What's your point of view? Well, many of the most important scientists have deeply experienced this connection between religion and faith and science, or faith and science. Planck once said, science and faith are not contrasting elements. They need each other to be complementary in the mind of a person who thinks in a serious way. In my experience, I must say that certainly my scientific work increases the prospects of faith. How? You know, nature, creation are a sign of mystery. And what is science if not capturing new signs, discovering more of how this is true? We can now enjoy beauties which we could not enjoy previously. Vice versa, faith is something decisive to me in that it motivates my work and gives it a certain sense and joy. I read Lumen Fidei recently. In this encyclical, I read that the faith reawakens the critical sense because it prevents research to be satisfied in its formulas or with its formulas, and helps it understand that nature is always greater. Faith is something according to which any answer is always partial. It always opens you up to what is beyond. This is a fascinating aspect in this connection and link, which I'm happy and I'm lucky enough to experience with so many friends. One last question about what you think about the future of space research in Italy. The Planck project was a leading one internationally, also thanks to the talents of Italian researchers that everybody envied to us. We know that our country would deserve better outlook than is the case. As a member of the Italian Space Agency, what do you expect and predict for our future. First of all, let me tell you that space science in Italy has always been one of the points of excellence in research. And this is shown by the fact that 10% of the world publications is made by Italian authors, compared to 4, 5, 6% in other sciences. Astrophysics is also part of space science and played a very important role for young people. At European level, as a member of the scientific committee of ENAF, I must say that space science is not affected by the global crisis affecting the world, Europe and Italy in particular, because it's protected by international agreements. The budget of ENAF, ESO and CERN were not affected so far. But in Italy, the source of funds for the space agency is undergoing problems. Italy is the third contributor to ESA after France and Germany. As a contributor, because of the international agreements which were signed by our founding fathers, there is a right or fair return. What we invest as Italy in ESA is returned to our industry. So Italy has some return. If you want figures, I can tell you that Italy contributes 400 million yearly to the budget of ESA. Then the Italian Space Agency, ASI, has budget deficits. Yesterday, the minister gave us no positive news about funds to research and education. This is bad thinking of our young people. The minister said it yesterday, 1 out of 2 persons below the age of 32 is unemployed. It's a dramatic situation. We have to start the economy in this country again, otherwise we can go nowhere. We know about the virtuous triangle of the economy, but we need to ignite this triangle of education, research and innovation. Otherwise we can't sell products abroad. We have to invest in research and young people, and increasingly so. The Italian Space Agency, ASI, does its best. The ESA scientific missions are paid by ESA. Well, this is what the bus. This is the bus. This is called the bus. So ESA funds the bus and all the scientific aspects. The member states fund the board instrumentation, which is paid, which is called paying cargo, as if the instruments were the passengers of the bus. Italy, concerning the Earth observation, has a microwave expand system, which is a radar with a synthetic opening. Italy, with this radar, is a world leader. It is a geostationary system developed for security reasons, but also for observing or for being ready in case of a disaster like the earthquake in L'Aquila. It works both at night, during daytime, and if the weather is cloudy. I think that unless the budget of ASI, the Italian Space Agency, is strengthened, we can do very little in terms of research and help to young people. Marco, you are the president of a foundation for education. What is the future of our students wishing to start a career in physics or astrophysics? First of all, the most important thing is that they desire to embark on such a career. If they feel that they have a desire like this, they have to take it seriously. The most important thing is to have an intuition and be realistic about it. We know that there has to be no hindrance to the free expression of a human being. One needs an international horizon to do this. It's important, therefore, not to feel restricted by your local boundaries, because the world is big. I would like to say that so far the Italian education and university system has been excellent. We have exported some of the best researchers worldwide. What we do here is train people who can do research in a very good way. Italy also needs foreign students, so it's not just about Italian students or Italian people going abroad. We can train foreign students in a very good way. There are difficulties in Italy, but they're not unsurmountable, in my opinion. The last thing I would like to say, in line with what Nazzareno said, is this. We're asking policymakers to take this issue seriously. That is, the possibility of training researchers in a full way. They can't train them in an exceptional way and then stop. We have to start again a tradition of training in physics. We can't lose a generation. If we lose a generation, we lose a bit of history. It would be a severe lack of continuity. I think this is my take-home message for all of you.
Grazie di cuore, grazie per la ricchezza.
Thank you very much. Thank you very much for the richness and wealth of this dialogue. Thank you very much for taking us along this journey in the universe so that we could admire it in a very global way. We are an enigmatic, the most enigmatic fruit of the universe. We depend on this cosmic symphony. We are only an infinitesimal part of it, yet we can admire reality. As Einstein said, the most ununderstandable thing of the universe is that it is understandable. This correspondence between the existing things and ourselves is taken for granted sometimes, yet it's something huge. Thank you very much, and please sign the appeal for the persecuted Christians. Thank you, and thanks to our guests.